Please welcome to the stage Carnegie Science President, Dr. Eric Isaacs.
Good evening, everyone. We're really delighted to have you here in our audience. We also have many people joining us virtually tonight, so welcome. We're in for a real treat tonight with our speaker, Professor Aomawa Shields will be talking to us, and I'll talk about that in a few minutes, but I really were excited. We also want to thank the AAAS for hosting us tonight. This is a beautiful auditorium. It's the first time we've used it, so we're really happy to be here. I will say that we have Carnegie has a long history with the AAAS. One of my predecessors was the editor-in-chief of Science Magazine for 20 years, which is one of the publications out of this place. So tonight, we're really delighted to welcome Professor Shields. She asked one big question, I think, which comes underneath a lot of things. She asked the question, are we alone in the universe? That also includes Earth, but rest of the universe. And I think that drives a lot of her science. And so we're really delighted to hear what she has to say about that. One of the reasons we're excited to have you, Professor Shields, is we also spend time at Carnegie, as you probably know, thinking a lot about exoplanets. And in fact, our host tonight, our interviewer is also in the planetary sciences. So let me tell you a little bit about Professor Shields. She's the Claire Booth Luce Associate Professor in the Department of Physics and Astronomy at University of California in Irvine. She's an astronomer. She's an astrobiologist, but interestingly enough, she's also a classically trained actor. And I'm sure the acting part is what underpins your passion for communications and for getting out there and talking about the wonders of science. At UC Irvine, she leads the team of researchers and educators in a center called the Shields Center for Exoplanet Climate and Interdisciplinary Education, where the research focuses on understanding habitability of planets that aren't Earth. We know we have life here, but what about planets outside our solar system? And that's one of their foci. She has a PhD in astronomy and astrobiology from the University of Washington, and that was in 2014. She has a master's in fine arts in acting from UCLA. It's one of the finest acting schools in the world. I don't know if you did that simultaneously, but I won't ask. And then she has her Bachelor of Science in Earth, Atmospheric and Planetary Sciences from MIT. I should mention she also went to Exeter as a high school student. Is that right? Exeter has one of the best astronomy programs in any high school. They've got a great observatory, so it was a great choice for you. Maybe that's what defined your future. So she's also had I can go through over a lot of things, but one thing I do want to highlight is the book, because you may have heard in our advertisement talk about Professor Shields that she wrote a book just recently, Life on Other Planets, in a memoir, which she talks not only of her astronomy, she talks about herself as an actor, a mother, and a Black woman in STEM. And we'll hear more about this when we get to the question period. The other thing I want to mention is she founded a really interesting science and arts program called Rising Star Girls, which is just phenomenal. Something that I know Alicia worries a lot about too, which is an organization that encourages middle school girls to explore and discover the universe using theater, using other methods, not just the traditional math and science. So it's going to be great. I'm sure everyone you teach is going to come. Now, I do want to take a minute. I apologize to you for a minute. I just want to highlight her mother, Dr. Shields' mother, because I'm really excited. And I don't know how many of you are huge jazz fans, but I am. And I didn't learn this until today when I was reading who was coming. And I saw that you were coming, which is Professor Shields' mother, Margot Simmons, who's a really fantastic musician. She created a band, she and a few of her colleagues created a band about 50 years ago called the Pyramids. And that was an interesting time in jazz. That was when people like Pharoah Sanders, Cecil Taylor, they were all creating this avant-garde, really interesting music with some mix of African in it. What they did, the Pyramids really brought that to light. They did an amazing, I started listening to it today because I really apologize. I didn't know about you before, but she was actually a student of Cecil Taylor's. If you know Cecil Taylor, you'll know what I mean. He's a phenomenal musician. And so I want to welcome you here, and I apologize to you because I'm sure she upstages you quite a bit. This has probably been your whole life, but I have to do it. And if you don't believe me about how great the music is, there is going to be a concert in the, what is it? It's going to be in the historic Walter Reed Park on Saturday. So you can always go see her yourself, and I don't have to keep going on. So a little bit of sort of clerical work. We're going to hear Professor Shields talk, and then we'll hear an interview, and I'm going to introduce Alicia Weinberger in a minute. What we're asking you to do, there'll be a Q&A, but instead of having live questions, we want you to put it in through this program called Pigeonhole, an app. So just use this QR code to get the app, put in your questions, and we're encouraging you because there's a great prize at the end. We have 5 books that are signed by Professor Shields, her book, which just came out last year. And you put in, the idea behind Pigeonholes, you put in questions you want to hear answered, and then you can either put in your own question or vote on someone else's question. And those questions that come to the very top will end up, the 5 will end up getting the prize, the door prize, which is a book that Professor Shields wrote. Now, I just want to very briefly introduce Alicia Weinberger. Alicia Weinberger, also she does planetary science. She's here in our campus right up in northern DC, the city, called Earth and Planets Laboratory. She's been here for a little bit of time, and she studies, her interest is also exoplanets, but not so much the planets, but how they form. When you look out in the stars, nearby us within some distance, you see thousands and thousands of planets, but she's very interested in the planets as they're forming, looking at these primordial disks of matter. And so she's been studying that, and she's an observational astronomer using amazing means. Fortunately, she won't get to say all of what she does today, but I just wanted to make sure you knew that Professor Shields and Dr. Weinberger are in very similar fields in many ways. So again, when you have questions, put them in throughout the talk. You can put them in, and with that, I would ask you to please join me in welcoming Professor Shields.
Good evening. I want to thank President Isaacs and the entire Carnegie Institution for Science for the incredible honor of being here today. And we're going to have some fun this evening. We're going to learn a lot of science. We're going to learn a lot about me, and we're going to do it in a way that's interactive. So the first, of course, you're going to be submitting your questions on this app with your phones. Before we proceed, I want to cover the most important part of this talk. So if you take away nothing else, to make sure that you know how to pronounce my name. Okay, so I've heard many pronunciations over the years, so don't be embarrassed, don't be shy if your first pass was not hitting the mark. We're going to do it all together. So first I will pronounce it. It's pronounced Aomawa. The emphasis is on the O. And so on the count of 3, let's all do it together. 1, 2, 3. Aomawa. Yay, that's great. You did great. That's literally music to my ears. And if you read the book, you will understand how true that really is. Because it's a song. There's a song too that goes with it. Okay, another part of the evening. It's something that you may not have done ever before in a talk, maybe never before at all. And that is, we're all gonna, what I call, rest in together. So this is entirely optional. You're not gonna get graded poorly if you decide not to participate, but I wanna invite those who are willing and would like to put down your phones and put away things that are in your hands, maybe clear off anything that's on your lap. Allow yourself to be completely comfortable. And for those who'd like to close down your eyes, or if you're not comfortable having your eyes closed in a public setting such as this, you can maintain a soft gaze. So you can keep your eyes sort of at a 45-degree angle towards the floor. So either way is fine. And if you prefer to keep your eyes completely open, that's also fine. And allow yourself to sink deeply into the seat. And notice for a moment the areas where your body is making contact with the floor or the chair. And what the nature of that contact is. The texture of the surfaces. Rough or smooth, Tune into the quality of your own breathing. Where do you feel the breath most strongly? Maybe your belly, your chest, perhaps the space right below your nostrils above your upper lip. Pick one place where the breath seems most strong to you and focus there. Notice the rising and falling of the breath, how it's like a wave. Belly rising, chest rising, belly falls, chest falls. And notice anywhere in your body where you may be holding tension unconsciously. Allow your belly to be soft. Shoulders soft. Relax the jaw. Let's take one full deep breath together. In through the nose. Sigh it out through the mouth. And gently wiggle your fingers and toes. And when you're ready, you can open your eyes. Thank you for participating in that. So we're all here because we care about space, and maybe we even care about planets. I know I do, because our planet orbits one single middle-aged star in a galaxy of hundreds of billions of stars, in a universe of hundreds of billions of galaxies. Just about every pinpoint of light in this photo is not a single star. It's an entire galaxy filled with millions, billions, hundreds of billions of stars. So at one point, this planet, our planet, was the only planet in the universe that we thought could ever support life. But we are living in a universe with a diversity of planets and planetary systems. And we now know of dozens of potentially habitable planets. While this is still an artist's depiction of one of those potentially habitable worlds, and this is as well, so these are artists' concepts. The hope is that one day this will not be an artist concept, but an actual photograph, like this is, taken by Ansel Adams of the Tetons and Snake River in 1942. We now know of close to 6,000 planets around other stars, which we call extrasolar planets, or exoplanets for short. And these planets are across a wide range of different regimes. And with the relatively new Transiting Exoplanet Survey Satellite, or TESS, this was Kepler's successor, we're going to be finding more and more. And TESS is an all-sky survey. So Kepler, which operated for nearly 10 years in various configurations, was staring at one particular patch of the sky and looking for dips in brightness of the stars caused by planets passing in front of those stars. Well, TESS is doing the same thing, but it's looking all around the sky. So it's going to find many more planets. It's also looking in the nearby solar neighborhood. So the planets that TESS finds are going to be easier to follow up on with missions such as the James Webb Space Telescope, which is already attempting to characterize and starting to characterize planets and the smaller and smaller regime planets. And we're doing this too with ground-based observatories, what we call extremely large telescopes, ELTs, in concert with hopefully next generation missions such as the Habitable Worlds Observatory, which is an infrared, optical, and UV observatory that's been earmarked by the Decadal Survey as a mission to prioritize, and it's going to be dedicated to looking for signs of life in the atmospheres of these potentially habitable worlds. So we're moving closer to what I consider the holy grail in the field of exoplanet astronomy, and that's the discovery of another habitable planet like the Earth that's capable of supporting and maintaining life over long time scales, and perhaps even currently hosting life. But there's an issue that we are coming up against, and it's a really high quality problem, I consider it to be, which is we're going to have hundreds of planets that are in this class of potentially habitable. And we're not going to be able to follow up on every single one of them to look for signs of life in their atmospheres. We won't have infinite telescope time. So we need a way to highlight the planets that are what I consider most likely to succeed in this category of habitability. And that's where my team's work comes in. So we use computer climate models to try to answer this question, are we alone? Specifically by highlighting and prioritizing and identifying those planets that we want to look at more closely, that have the ability to maintain and sustain habitable conditions over long time scales. These are the same climate models that were used and are being used to predict, first to highlight the presence of anthropogenic, that's human-made, carbon dioxide-induced climate change, and have been projecting it into the 2100s. But what we're doing is changing certain knobs in these models. It's enabling us to simulate the potentially habitable climates, the climates of these planets by changing the host star. We can change the atmospheric composition. We can change the orbital characteristics of the system, and that can allow us to predict climate and weather patterns on exoplanets. So yes, this is one way that you can look for life, and I'm glad that people recognize, like, who's seen this movie here in the audience? Thank goodness, there's a lot of hands. Okay. I shared this picture in my Life in the Universe undergrad classes at UCI, and I asked for a show of hands for who's seen the movie, and no one raises their hands, because no one was born when this movie came out. So I give them an assignment. So, but it's a wonderful movie. It's an even better book. And you know, Jodie Foster's character Eleanor Arroway is listening for the signs of life, through radio signals of that life. And that's one way to do it. The way that we do it is using observational data where it's available and when it's available in concert with computer models, these computer climate models. And that allows us to be able to really, this two-tiered approach gives us that opportunity to identify these planets that might be habitable, and also to think about fun, exciting new scenarios that planets could actually occupy in space that we haven't even discovered yet. So when I've been using that word habitable a lot, and I want to talk about what that means. Our main criterion for habitability is the presence of liquid water on a planet's surface. And of course, that's not necessarily the only way that life could survive in the universe, but on our planet, it is. Life on Earth has a diversity of metabolisms, and every single life form, from the tiniest microbe to the largest elephant, requires liquid water for chemical bonding and as a solvent for chemical reactions. So liquid water is truly what drives the search for life elsewhere. And so when we think about kind of the question beyond are we alone, we have to get more granular. How and what influences liquid water on a planet's surface? That gets pretty complex pretty fast. There are a lot of different factors that can indicate and govern the long-term presence of liquid water on a planet's surface. The stellar and planetary properties, the unique environment of that planet or planetary system. And so many different teams within our field try to sort of chip away at various parts of this web, I like to call it. The parts of the web that have impacted me and have interested me over the long term is a couple things: stellar effects, the star's environment, and how its light is distributed with wavelength. Not all stars are created equally, and not all stars emit their light equally. So I know we have a very diverse audience here in the room. Some of you might be astronomers or planetary scientists. Not all of you are, so I'm going to provide a brief primer on stars, because as one of my colleagues, Lucianne Walkowitz, likes to say, behind every planet, there's a star. Let's not forget that it all starts with the star. Okay, so stars come in all different colors. And that's the motto of Rising Star Girls, right? Stars shine in many colors. So our sun is a G star, it's right here. And I'm going to direct your attention to a couple of other classes of stars. So the M stars, red M dwarf stars, much cooler and smaller than the sun, and the most numerous type of star in the galaxy. 70% of all stars are these M stars, M dwarf stars. And M stars have a lot of advantages when it comes to looking for life on planets orbiting different types of stars. People think like M's are the ones we want to look at. One of the reasons why I would agree with that is that M stars, because they're so small, low mass, and mass says everything about a star. Mass governs how a star lives, how it's going to die, how it's going to evolve. It's all about mass. And these small stars are the tortoises of the stellar family. They burn through their fuel very slowly. And so they live for a long time. So and for a long time, I mean hundreds of billions, and in some cases, trillions of years. So long that in fact, no M stars have ever died, because their lifetimes are longer than the current age of the universe, which is just shy of 14 billion years. And these lifetimes are hundreds of billions or trillions of years. This is one of the reasons why we're excited about the prospects for life around M stars, because their lifetimes would offer plenty of time for both planetary and biological evolution. Especially when you contrast that with the O stars, which are like the James Dean of the stellar family, or the Amy Winehouses of the stellar family, like that 2027 club, I think it is. Right? They live fast, they die young. They're like the Humvees also. Like, I'm just gonna give you more and more analogies. Right? They live for maybe, millions of years. Right? That's not very good from a habitability standpoint, given that it's believed to have taken life on Earth about 500 million to 1 billion years to get a foothold. So M stars have a lot of advantages. There are also some disadvantages that I will at least mention as we go further. So starlight, I have been interested and really infatuated, I must admit, by a star's light and how the light from the star could influence a planet's climate. How that light changes given whatever star is being orbited by that planet, and how that light can come down from the star and interact with planetary gases in the atmosphere, surface types, and how that interaction simply can govern a planet's climate. As a grad student, the main thing I know I wanted was to find that topic that would make me want to work on it for 6 years. That I need at those 6 years that you need to work on something until you get a PhD in it. because no one's gonna get you up out of bed and say, go work on that thing. You have to find something that really lights you up inside. And I was fortunate that I walked into a journal club. I think it was my second year as a grad student, and a more senior grad student was giving a talk on this paper. It has a really long title. Suppression of the water, ice, and snow albedo feedback on planets orbiting red dwarf stars, also called M dwarfs, and the subsequent widening of the habitable zone. So this paper was my bingo light bulb moment, because water, ice, and snow, I came to discover, has this spectral dependence. It doesn't behave the same way towards all types of light. And that felt very personal to me, because as I'll talk about a little bit later, I didn't really fit a common mold. And I had these at the time, they seemed seemingly disparate interests, and I wasn't quite sure how to reconcile them. And so I thought, well, this is me in journal article form. I want to study this. So when we think about ice albedo feedback, we typically think of ice as being a very bright thing. And the more light that ice reflects, the less it absorbs, the colder the planet gets, more ice forms, reflects more light back to space, etc. This is a positive feedback. But water ice likes to absorb longer, redder wavelength light and reflects shorter, bluer light. Anyone who's watched my TED Talk already knows this, but this is why this iceberg looks so blue. It's right, the red light from the sun gets absorbed on its way through the ice, the red and infrared light. It's only the blue light that makes it all the way down to the bottom of the iceberg to get reflected back up to our eyes, and we see a blue iceberg. So we can see examples of different types of behavior and different, certainly just qualitatively by eye, the colors of different types of ice purely due to grain size on our planet. Those larger, coarser grained ice surfaces, like this beautiful blue marine ice here, right? There's not very many cracks in that ice, so that light is able to go all the way down to the bottom, and that red and infrared light getting absorbed, and that's why we are able to see that blue color. But the finest grain type of ice, which is snow, there's so many fine grains that there's a lot of scattering happening, and we don't see that blue color. Instead, we see white. So we can see this kind of different behavior on our planet, but that behavior can be even more acute on other planets that are receiving light at different wavelengths from other stars. One of the most exciting things and discoveries in this field has been the realization that our solar system is not the standard model, but one example of many possible configurations that we're seeing out there. And so our work, I'm going to highlight a little bit of what we've done to explore these kind of off the beaten path scenarios and habitability regimes that are possible out there. For example, this green area here is called the habitable zone, that Goldilocks zone, the region around a star where a planet might be warm enough for liquid water to stay liquid. If you have a planet that's orbiting a star, not in a circular way, but in a very elongated oval-shaped orbit, it may veer within and way outside of the habitable zone throughout its orbit. When it's within the habitable zone, it might be nice and clement, like our Earth, by and large. When it's way outside, it could completely freeze over and then back again. What would that do for life? Could life even exist within those tumultuous conditions? Well, our team was able to explore what we call the eccentric habitable zone, and that term was not a new term, but what we found was that the eccentric habitable zone is sensitive to host star spectral type. So we found this is looking at how elongated an orbit is. If it's 0, then it's a circular orbit. If it's 0.9, it's very, very oval shaped. And here is how much light the planet's getting from its star compared to the Earth, which is here. And as we're seeing, if you've got a circular orbit, the planet has quite a bit of habitability. This is how habitable, above freezing surface temperatures, your planet is, given different eccentricities or orbit shapes. And so yes, the circular orbit gives you a lot more fractional habitability, But even for these very elongated orbits, we see there's some point in a planet's year over its orbit where it does exhibit above freezing surface temperatures. So even the planets on these really highly elongated orbits, they can be habitable for some portion of their year. And we find that if the planet's orbiting a cooler star, it's going to have a larger swath of habitability. So understanding that starlight is really impactful when it comes to these processes. And looking at the different stellar environments is pretty critical to understanding fully their habitability. Coming back to these M's, and I said I would, there's a lot of area to explore. The thing about the habitable zone, and this is showing it to you not as a green swath now, but as a blue swath, and extended, elongated. We've got for different types of stars, the cool M's down here, and this is the sun right here, and how far away a planet would need to be. That blue swath is the habitable zone. So planet needs to be there. In theory, that's our 0th order approximation. We know it's not all about orbital distance, and that web I showed you proves that. There's a lot more at play when it comes to habitability than simply how far away a planet is from its star. But this is the first step. And certainly when an observer finds a planet, they say, okay, we found a planet, it's in the habitable zone of its star. That means it's potentially habitable. And then those of us who are computer models, that's when it's our turn. We need to say, we'll tell you exactly how habitable your planet really is, given various atmospheric compositions and things that you can't yet constrain with observations. But looking by eye here, this habitable zone is much closer in to a cooler, smaller star than a hotter, brighter star. And that makes sense. It's the same principle. If you're at a beach and you're crowded around a little campfire to stay warm, you wouldn't have to crowd as close if that was a bonfire than a little tiny campfire. Same principle at work here. So when you're that close to your star, a lot of interesting things can happen. Among them, with M dwarf planets, so planets orbiting these M stars, they could get tidally locked, which is a general term, meaning that the rotation rate of the planet is being slowed down by the gravitational interaction it's having, the gravitational force that's existing between the planet and the star, right? The closer you are to that star is pulling on the planet, slowing it down, and that tidal locking is happening. An extreme case, in fact, the most extreme case of tidal locking is called synchronous rotation. And that's also a 1-to-1 spin orbit resonance, which means that the planet's day is equal to its year. The time it takes to spin around once on its axis is equal to the time it takes to travel once around the star. So day is equal to its year. A lot of people confuse tidal locking with synchronous rotation, and in fact, use the terms interchangeably, and they are not in fact the same. All synchronously rotating planets are tidally locked. Not all tidally locked planets are synchronously rotating. So this synchronous rotation could be a problem. Could be that the planet gets so hot. Essentially, this means that there's an entire perpetual day side. One side always facing the star, and it's perpetually day. The sun never sets. On the night side, it's perpetually night. Sun never rises. Could get so hot on the day side that it's inhospitable. Could be so cold on the night side that the atmosphere completely freezes out onto the surface, inhospitable. So what to do? What would life be able to do? How could life even survive on that planet? It turns out, and it's more nuanced than that, and it turns out there's ways that you could actually have habitable conditions even for synchronously rotating planets. Perhaps if you have enough of an atmosphere, you can distribute heat from the day side to the night side to even out those extreme temperatures. But what we were concerned with and really interested by is the question, say you did have too hot of a day side, too cold of a night side to be habitable, and the only place you could have a hope of above freezing surface temperatures was along the dividing line between the two sides, which is called the terminator. Right? Da, 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 da. So my postdoc, Anna Lobo, and I have been looking at this, and we did look at it and published a paper that found that, yeah, you can have planets that are Terminator habitable. And it's actually quite difficult to create in climate models a scenario where you're too hot on the day side and too cold on the night side. That the only place where you're warm enough but not too warm is along that dividing line. But it's much easier to have that scenario if the planet has not as much water. So if they're water limited. When you have an ocean on a planet, you're either going to be so hot everywhere that you're going to have what we call a runaway greenhouse, where we think that's what happened to Venus. And hopefully not us, but we are headed that way if we don't do something about our climate change issues. That if you have less water, it's easier to have these extreme conditions and only that Terminator scenario there. And so it was so much fun to be able to create these scenarios that we haven't yet identified out in space, but we know could exist and actually could be more likely to occur for planets orbiting M stars, because they start off probably water limited in the first place. They're smaller stars, they come from smaller protostellar nebulae, and there's less what we call volatiles, less water available to begin with. So these scenarios might be the most likely condition for or population for these stars, planets orbiting stars in the future. So that partial habitability, again, Terminator habitability, where you're only habitable along that dividing line between the light and the dark side. We were able to then discover that this regime applies not only to M dwarf planets, but also to the K dwarfs too, planets orbiting stars that are a little bit larger than M's, but not quite as large as G's, like our sun. So they're orangish color. And we find that it's harder, well, I can answer more about that in the Q&A, but we're more likely to find these planets orbiting K stars in what's called an eyeball regime, an eyeball Earth, where you're frozen everywhere except for an eyeball region on the day side, than having them in a Terminator habitability regime. And I can certainly elaborate more if you're interested in knowing why. And then, of course, what's nearest to my heart is really thinking about surface types, surface compositions. So when we think about our climate models, it can be easy to go to, let's just make sure that the planet has an ocean everywhere. It's simplest, and we'll have an idealized scenario and leave it at that. But of course, we have only to look outside of our windows to know that there are a lot of surface types possible on planets, everything from water to dune sand to granite to calcite to salty ice to completely saltless ice. There's all sorts of different types of surfaces and compositions that could exist. And it's important to understand their specific feedbacks, climate feedbacks, and interactions with, and how the host star's light can in fact impact those interactions. The surface does matter. And I've been a champion of this for a while. I think in the past, the observers have thought, well, we can't tell what's on the surface yet, so why is that important? Well, we've been able to show in the climate simulations that in fact, it's quite important. And when you have different surfaces and you run your simulations, we find that the climate is definitely different depending on the surface reflectivity pattern and parameterization that is entered into these climate models. We've applied these principles looking at different surface types to the TRAPPIST-1 system, a very exciting system of 7 Earth-sized planets orbiting a star called TRAPPIST-1, which is an ultra cool M star. And we've seen, looking at, so these are the spectra, so how the light is distributed with wavelength for different types of stars. This is the sun in yellow, a star that's hotter and brighter than the sun in blue, one of those K stars in orange, and this is TRAPPIST-1, that ultra cool M in red. And then down here is how reflective different types of land surfaces are. We have a really reflective calcite surface. We have snow and a more absorptive water ice here. We've got granite, dune sand, a clay-like substance called iridisol. And we see that just by looking at, with our simulations, the different surface types, we can see as much as 50 Kelvin, 50-degree difference in our resulting climates. We also see that cross-equatorial heat transport is definitely affected by the albedo of the surface. And that allows us to understand that perhaps TRAPPIST-1d, for example, is the most likely habitable planet within this system. And we're able to do that by exploring the different range of possible land surfaces, and in the future, other types of surfaces that could exist on these planets. We also, in the past, were interested in, we always assume that the ice is water ice, and that's it, and it's pure water ice. But of course, water ice could have all sorts of different compositions within its matrix. And an example of that is a composition called hydrohalite, which is very, very salty ice. And hydrohalite could precipitate within bare sea ice at low temperatures. And look at how reflective hydrohalite is in the near infrared and compared to pure water ice and snow, which gets very absorptive at those longer wavelengths. Not so for hydrohalite. And we were able to show that when you incorporate parameterizations for the formation of this particular surface type into climate models, we see that for planets orbiting M stars in the habitable zone, they can get cold enough for this surface type to form. And if we don't have these parameterizations in climate simulations, we would underpredict the climate of these planets. Let's get back to the eccentric planets for a second. So as I mentioned, these planets could be very clement and comfortable temperature-wise in the habitable zone, and then veer way out where they could freeze. We could have a lot of different exotic ice surfaces beyond water ice when they freeze. And my grad student, Vidya Venkatesan, has been looking at this at length, because of course, beyond water ice, we could see, if the atmosphere is freezing out onto the surface, we could see things like carbon dioxide ice on top of that water ice, methane ice on top of the carbon dioxide ice, and so on. And she's been able to find that we certainly have different albedo spectra for these different types of ices. And so CO2 ice, which is highlighted here, again, very reflective in the infrared, where the pure water ice becomes extremely absorptive. And so what we see when we incorporate parameterizations for the formation of CO2 ice into climate models is that even planets at moderate eccentricities can get cold enough for CO2 ice to form. And we need to have these parameterizations in climate models and all climate models to be able to accurately understand how habitable eccentric planets are, or planets that are on circular orbits, but at very wide orbits far from their stars. And finally, research-wise, something that I've been quite interested in is white dwarf planets. So white dwarfs are a class of star that haven't been explored that much until recently as potential hosts for life, because simply white dwarfs that's what's going to happen to our sun eventually. It's the end stage of stars like the sun. The sun will eventually become a red giant and engulf the inner planets, and then it'll become this planetary nebula, and then it's basically a big exploding star, and at the very core will be a white dwarf that is no longer undergoing nuclear fusion in its core. It's going to be cooling with time, just like a dying candle flame. And people have thought, well, there's no way you could have planets formed around these white dwarfs, because most likely the planets would have been engulfed during the red giant phase. But recently we've been thinking about potentially either the planets that are far away from the original sun that never get engulfed. Perhaps they migrate inward and become the new habitable zone real estate for those white dwarf planets. Or perhaps planets form in situ from the wreckage of the earlier progenitor. And so it's allowed us to think about what truly the environment could look like in the habitable zone of a white dwarf star. And so I took liberty here with Chester's plot and added, so this would be, we've done a comparison of a regular normal K star, which would have, if a planet's in the habitable zone of that star, it would exist out here. Whereas a white dwarf with the same temperature, right, it's going to be similar mass, but super, super small. I made that big so that we could at least see it. And its habitable zone planet would be way close to its star. Because remember, it's a dying flame, dying ember, cooling with time. So a habitable zone planet has to be right up close to it. Therefore, it's going to be spinning really fast because that rotation, it's going to be a lot of gravitational force. It's going to be spinning fast. Its day is probably going to be like 10 hours. And that's also going to be its year. And what we did was compare, and this is a snapshot of some soon to be submitted work, so very, very fresh, looking at the temperature of these planets. So again, the planet orbiting the regular normal star, which is also synchronously rotating, both of them are, but look how different their patterns are, right? This is that kind of one side, the day side, eyeball Earth type thing. And this one has this sort of lobstery, bat-like appearance. And what we find is there's warmer surface temperatures on white dwarf habitable zone planets than the planet that's around what we consider a normal star. So taking a step back, I've been talking a lot about the research that I've done, and I think it's important. As when I was younger, I was really interested in how people got to be able to do the things that they're doing. Like I needed to connect the dots there, because in my mind, people seemed like they kind of emerged from the womb fully formed and adults doing their stuff, their professional stuff. But I needed to understand how did you get to where you are? What are the different steps that you took to become that? And of course, you can read all about it here in this book, and I hope that you do. And I'm going to highlight a few vignettes from it tonight. But I wanted to call this last portion of the talk How I Became an Astronomer and Astrobiologist. So this is my grandmother, and she majored in math at Tennessee State University in the 1930s. So yeah, I have to let that settle in. As rare as Black women are in STEM fields today, we think about that in the 1930s, it was pretty non-existent. And though she did not finish, she passed her love of math on to me. So Tennessee State University was an historically Black college at the time, and she was in this classroom with all Black men, and she was never called on. She was ignored like a shadow, and she put herself through school by selling chickens, and one day the chickens escaped, and that was the end of her college career. But when I knew her, she had this stack of accounting textbooks on her bedside table, and she went to night school. She was a civil servant at Miramar Air Force Base. And I wanted to, so Miramar was where, that's where the movie Top Gun was filmed, the first one, the original one. And we lived out there while it was being filmed. And my family would go and go to the flight shows of the Blue Angels because they were also based there, the aerial flight team. So I'm reading a section from the early part of the book here. I would watch the skies piercingly clear crystal blue, punctuated with fluffy white streaks of contrails. That blue was a feeling. I would lie back on the soft checkered blanket and feel as I watched. I felt the tiny hairs of my arms warm and sink closer to my skin and release, relaxed by the temperature of the sun. I didn't know then how truly unique the sun was. its yellowish, whitish glow so uncharacteristic of the vast majority of stars in the night sky, which are mostly redder and cooler and smaller. Then I simply felt comforted by the blue as I watched the planes dive and curve and make patterns and shapes that I could hold out my fingers to trace. The blue was for me, so that I could see these planes in the sky, so that my family could live and work and enjoy something special on the weekends with the rest of San Diego. No place else existed. In no other town or state or country was the blue this blue. I wouldn't truly understand how the sky got to be that blue until graduate school, how it wasn't from the sky reflecting the color of the ocean. The blue is everywhere, over the Sahara just as well as over the Mediterranean, how the sky is an atmosphere, how the tiny pieces of that atmosphere are really good at scattering blue light from the sun much more than any other kind of light. How humans have only known this for a little more than 150 years. All that time before, not knowing what caused the color over our heads. When I found out, the new knowledge was an emerald jewel I kept inside my body, warm and glowing near my heart, with a thin silk thread connecting it to my mind. I could never not know this now. So this is a picture of my mom and me. My mom sitting here in the audience today. And this is, I was not the first person to get a PhD in my family. That distinction belongs to my mother. And this is, we are at her master's degree awarding ceremony though, just to be clear. She went on to have another child after me, my brother, and did all that and got a PhD at the same time. I have no idea how that happened. Yeah. This is my dad, and he's also going to be performing with my mom and other whole other band members at the Home Rule Festival on Saturday. So do come out and see them. It's going to be a fun show. He's an incredible businessman, claims to have never had to have a day job, and yeah, really instilled a strong work ethic into me. And this is one of their albums. So my parents were in this band called the Pyramids. That's still their band today, one of their bands. My mom also has another one of her own. And can you find my parents in the album? There they are. There they are, several albums since. When I was 12 years old, I saw the movie Space Camp. And this movie, though not an Oscar contender, changed my life in every way. It's about a bunch of kids who get accidentally launched into space on the shuttle while they're at space camp, because it's always possible when you're at space camp that you could get launched into space. And I ran home that day and pulled out my World Book encyclopedias, and I had a set that looked exactly like this set. And I pulled out the volume labeled A, and I looked for astronaut and read all about astronaut and astronomer, and I plotted out my entire career trajectory that day at the age of 12. I was going to go to MIT and major in astronomy and get a PhD and then apply to NASA. And I stayed pretty close to that trajectory. This was me at Exeter on the floor, I don't know, playing with my feet or something, but I had the MIT sweatshirt on, I was ready to go, and you know, then what I hadn't accounted for was life. Life happens. And I ended up stumbling into an audition for play Steel Magnolias with some girlfriends, and I ended up getting cast when I didn't even care if I got cast. And of course, then I got cast, and it became, you know, one play after the next. And but you know, I was very driven and wanted to stick to what I had decided when I was 12. So I decided I was going to still go to MIT, and I did. But I had this conflict, which was like, I loved these sci-fi shows and movies, and I wasn't sure if I wanted to be doing what the actors themselves were doing or what the characters the actors were portraying were doing. And I looked around. I started a PhD program in astronomy at University of Wisconsin-Madison. I looked around, and I didn't see anyone who looked like me. They all looked kind of like this. So that affected my choices. And this is a little vignette from the book where I'm at Madison. Without a common center of mass, a moon will not revolve around its planet, nor will that planet orbit around its host star. Rogue planets do exist without stars to warm them, but these planets hurtle through space in darkness as cold and barren wastelands. I'll tell you more about them later. Planets, like ships and people, need a force of attraction to anchor them. The force between the Earth and the moon keeps both together, bringing us tides to rise and swell up in the oceans. The Earth never gets carried away by them, though. The tides are strong, and the Earth is too. The force between the moon and the Earth creates that powerful anchor. Anchors hold bodies firmly planted in time and space. Anchors connect a body to the ground beneath, to something bigger that guides and protects, filling it from the inside out. Anchors prevent bodies from hurtling coldly through space into black holes of loneliness from which there is no escape. So at that time, I sort of did everything wrong at Madison. And I think it's important to mention that because often, again, I think young people think the adults made all the right choices and then, the end, they're successful. But that wasn't my experience. When things got hard, I hid instead of asked for help. And then I escaped. I escaped to Hollywood. I decided I was going to follow that other dream that I discovered along the way. And I got into UCLA, and Eric, I didn't do it at the same time. I ended up just leaving that program and starting a new one to get a master's in acting. And I did some incredible things. And it's like, yeah, mistakes were made and wonderful things came out of them. If I hadn't done this, I wouldn't have met my husband or have the daughter I have now. So you just never know. I acted in a film called 9 Lives that went to Sundance and was one of Ebert and Roper's top 10 films of 2005. Did a science TV show, acted in Greek tragedy, which this is me as Andromache in the Trojan Women saying goodbye to my son who's about to be flung off a cliff because that's what happens in Greek tragedy. But I realized the most exciting thing that I wanted to play character-wise was myself. And I ended up taking a day job, working for the Spitzer Space Telescope, which was another one of NASA's great observatories, but it had infrared eyes instead of visible eyes. So it was up in space like Hubble, but it was really good at looking at young star formation and the dust between stars. And that really allowed me to fall back in love with astronomy again. And by that time, almost 11 years had passed, and an entire field of exoplanets had bloomed. And that's what I wanted to study. So I decided to exchange my life in Hollywood for a second bid at a PhD in astronomy, this time in the Pacific Northwest. And gosh darn it, I was going to finish that one. And I did. And this time I did all of the right things, or the things that, not that there's right or wrong, but the things that helped me progress. Asking for help, joining mentorship programs. There was a process group for graduate women of color that was facilitated by a Black man, mental health professional. And he just made a safe space for us all to come in once a week and complain, basically, about how hard it was to be grad students and balance what we're doing with our personal lives and trying to do it all. And that was crucial. And there were mentorship programs there was one called MS PhDs that was created by Dr. Ashanti Johnson, a chemical engineer, or excuse me, a chemical oceanographer. And she had created this program that allowed us to literally we were in a room. I was in a room with 30 other Black and brown faces, and no one was the minority. If a white person had walked into the room, they would have been in the minority, and none of us had that experience before. And I had a mentor in that program, Dr. Akuya Asa-Uwuku, who's was at UC Riverside at the time, and I think now she's in New York. But she told me to view my theater background as my superpower. And when I went back to UW, went back to get a PhD and was at UW, I sort of thought I had to sweep the theater background under the rug to be considered, a serious scientist. People would ask me about my background in arts, and I kept deflecting. And when she said that, your theater background is your superpower, it totally changed everything for me. So I finished that program, and this is me at my PhD hooding ceremony. Thank you. And this is my husband helping me with my hood. And that day he had like 103-degree fever, but he was not going to miss that ceremony. And this was before COVID, so you could show up with 103-degree fever and nobody had any problem with that. So he was there. This is my dad. I swear we did not coordinate. He is that fashionable. He just is. And I also want to show that, as a professional scientist, as a writer, yes, life is full. And part of the reason why life is full is because I have a life outside of work. And it's also important for, I think, young people to know that you get to have a whole, full, three-dimensional life and be successful. You don't have to give away your personal dreams to be professionally successful. And you can even work a 40-hour week and be successful. You can. I have. And it's something that people are not going to brag about, because there's a culture of the harder you work, the more accolades you get, right? And we get to push back at that and say, no, I'm going to work softer, not harder. And in fact, that allows me to work to be sustainable in my life, and to be able to have a life, and to be able to be around and stay in my life, and have a long life, so that I can hopefully be around and actually help make the world a better place. So although this is one way that one can and people have searched for life, I hope that I have allowed you to see that there are many ways that that can be done. In particular, using these climate models to imagine and dream and explore. And as that holy grail gets closer and closer to us, let's also remember that there's other generations that are important to nurture so that they can be part of this quest. And this is one way that I'm hopefully contributing to nurturing that generation. And it's with this program called Rising Star Girls. So these girls, middle school girls of color, are learning about astronomy and astrobiology, and they're doing it using their own personal backgrounds. We want them to know that they get to bring their whole selves to what they're learning. They don't have to leave their whole selves at the door, at home. We want them to bring who they are. They get to write poems and draw pictures about what they're learning, and bridge that dividing line between professional and personal, so that they can feel like they're a part of this. So when they look up at the sky, they can say, I wrote a poem about that star or that galaxy, and that they can have ownership of that, so that when the heavy math and science comes in, as they accelerate through the academic ladder, they'll be less likely to turn away from the field just because it gets hard. So we're trying to develop that personal connection for them, because just as if we were to look at the Milky Way in only one type of light, we'd miss out on so much compared to looking at it in different types of light, like the infrared here. So too is there much more to these girls than what meets the eye. So they're making their own artist concepts of NASA remote sensing images. They're creating their own constellation myths. They're learning that constellations are merely patterns in the sky created by different cultures, Western, yes, but also indigenous cultures and African cultures and Asian cultures. And they can create their own constellation myth stories too. They can design their own exoplanet environments and make choices about these planets, like, do they have life? If they don't have life, why? If they do have life, what kind of life is that life? How many stars does the planet orbit? And they can discover that, wow, there might actually be a planet out there with the exact conditions that they've designed. So we've been conducting virtual workshops through the pandemic, and now with our Heising-Simons Foundation funding, we're now moving back into in-person along with our virtual workshops, which allow us to reach girls all over the world. And we train educators to conduct Rising Star Girls activities in their own communities because we have a handbook that you can download for free from the Rising Star Girls website in both English and Spanish. This is the Rising Star Girls website, and we'd love to have people involved, whether through donations or through in-kind support or simply as champions of this work. We'd love to have you as part of our community, and there's an email listserv you can subscribe to. Make sure, whether you are a young person or not so young, but still interested in learning, continue to do that. Don't ever stop learning about yourself and loving what you discover. Develop your own values and trust them. This used to be my motto, my, what's that word? Mascot. And now, this is my mascot. All right, I'm trying to remember to slow and soft. And this is something I've trained now, and I will be certified quite very soon as a Daring to Rest Yoga Nidra facilitator, where I lead people on, and will be this fall conducting the first rest workshop on my campus for faculty, staff, and grad students. And this could be you. So I've done this at Caltech last month. It was successful. So ask me more about it, because whether you're on a campus or not, you can have Yoga Nidra in your life, and 30 minutes of Yoga Nidra is believed is equivalent to 3 hours of sleep in your body. So who wouldn't want that? It's been a game changer for me, and practices like these can help us go from maybe this to this, or perhaps even this, more of this in our lives. Like, who wouldn't want that? Okay. Thank you all for your attention.
Thank you so much for bringing your whole self to us today. We have so many good questions in our pigeonhole. I think, are going to stop upvoting now so that we get an honest vote on the 5 people who will get a copy of Aomawa's book.
Perfect.
How did I do? Okay.
Yeah, great.
I have to confess, I listened to the audio version of your book, so I could hear you say it before.
That helps.
So despite the fabulous questions here, I want to ask you one question of my own, because in the early part of the book, you talk about how excited by collaboration you were in the theater, and how that really brought something to life that was greater than the sum of the parts. And I wonder how you feel about collaboration in science and astronomy and astrobiology, and whether you have any great tips for those of us who do astronomy as careers from that collaboration that you learned as an actor.
I love that question. I enjoy collaboration too in astronomy. And I mean, this idea that astronomy and acting were so far apart, I no longer believe that now. I see how much creativity there is in science. And there was one section I didn't read from the book that I thought I might, but I'll tell you now. It was this idea of story was the common thread for me. And astronomy is about story too. Except the characters are not humans or animals. They're stars, galaxies, planets. They have their own stories too. They live and then they die. And it is exciting to work on these finding out what stories the data, which our characters, the data are telling us with other people. As a scientist, some of my work can be done with the computer on my own, but most of the time my papers they're collaborations. There are people that we work together, and it's important. I think what I tell my team members and my students is establish everything as much as you can at the beginning, like who's going to do what, the roles, responsibilities, including those hard conversations, like who's going to be the first author, the first name in our field, that the first author is the person who does the most work. In some fields, like I think math and maybe biology, it's the last author is that. But whatever that is, decide those roles early on. That idea of communication is so important. When we don't talk about these things up front, it can lead to assumptions and tough feelings. But I really enjoy it because I find, and astrobiology is really key to that. I learned how to collaborate really by working with other astrobiologists. And it's great because it's not like we all have to go get a PhD in every single discipline that's going to be brought to bear on this question, are we alone? We can't. It would take us more than a lifetime to get all the PhDs required. We don't have to. We can say, okay, I worked with a glaciologist who had her expertise in glaciology, and I had the astronomy expertise, and we were able to combine them to talk about this paper on hydrohalite stuff. And that allowed us to be able to bring each of our strengths to bear on a common question. So it's really powerful.
Thanks. Well, there are a lot of questions here about astrobiology, so
Okay.
let us get to some of those. So first, of course, is life is very complicated to define. So, of course, habitable is not the same as inhabited, and you made that point. But this question from Marvin asks, what is your definition of life, and how does it inform your work as an astrobiologist?
Oh, wow. In my Life in the Universe class, we spend a couple of classes talking about this because it's really hard to define life. And there have been whole textbooks on this subject. Because you can't say it definitely reproduces because there's, we have, it's not mules, it's donkeys, right? I always get them confused. These are mules or donkeys that are sterile, so they can't reproduce. And so we can't say life has to reproduce because then you're leaving out something that is alive. Viruses, it's a very gray area because they need a host, but yet one would argue they're at the intersection. But I would say some key characteristics are, having some sort of awareness, some sort of sentience, being able to take in information and I was going to say feed, but take it, nourishment, energy, produce and energy, use energy. Those are some of the, off the top of my head, the characteristics that are there, and informing, understanding that I think what's been helpful and we find is most helpful, even more so than what is life need. That's most helpful for us because of these exceptions and gray areas. When we think about defining life, it's a little more straightforward to think about what life requires. And there's three things on our planet. It's an energy source, whether it's stellar or chemical, and a suitable environment for the formation of complex organic molecules from what we consider bioessential elements like sulfur, phosphorus, oxygen, nitrogen, carbon, hydrogen. We can call that SPONGE for short, and liquid water. Those are the three major requirements, and that's been most helpful for me from an astrobiological standpoint.
So that is related to, so using us as an example is related to a couple of other questions on here. And one that I like from Monique, she asks, super Earths and sub-Neptunes are the most commonly found planets in our galaxy, but are starkly missing from our solar system. Could the why our solar system is different provide insight into exoplanet habitability?
This is why we've been learning this going out to these other solar systems and seeing those classes that were mentioned, so true. We don't have an analog within our solar system for these different regimes. Same thing with hot Jupiters. These are Jupiter-sized planets that are searingly close to their stars. We don't have those here, and yet we see them in other systems. And how did they get there? And so it's definitely helping us we have to expand our solar system formation theories. I bet you have a good answer for this one.
I know, but I plan to spend the rest of my life trying to figure it out.
Right?
Well,
Yeah.
so how unique is our system, I think, is what a lot of these questions come down to. Like, are we really special? Or are we going to find out from our study of M stars and all these different kinds of planets that the anomaly is what is common?
This is an open question. we have seen so many different types of solar systems, enough to tell us that we are not we are not the norm. And we have people who've written books called Rare Earth that are saying that it's probably just us, and it's because things happen in a certain way that would make it unlikely that they would happen elsewhere for life to start. I like to subscribe to the Contact view, the line from Contact where Eleanor Arroway says, if it's just us, it'd be an awful waste of space.
So similarly, Danny asks, well, will it matter to us if we do discover life on another planet, but that life is very far away? Like, what do you think the impact on us would be, or on us as a people, as a species, as an inhabited planet, if we were to find life on another planet?
I love these.
You're asking to be a philosopher as
yes.
well as an actor.
Well, and I'm not trying to like resurrect this movie again, but I'm going to mention it again because that movie in the book is really powerful, because it talks about the question is answered, and that's like the beginning of the story. And this is a similar question. If we find out that we really are not alone, even if that life is way, way far away, as it was depicted in the movie, what would that do to us as a species? Some people were super excited in the movie, in the book. Other people were incredibly afraid and took drastic action based on that fear. I would be, I don't know, I can't say how I would be, but I know that that excitement would be there. And I suppose if the life is far away, it would give us some time to think about, what we would, versus like they're coming, or we have to go. But I think it would be an incredibly exciting question to have to answer.
So do you think that your experience becoming an astronomer, or your cultural background and identity, help you discover new questions to ask that are different than the questions that other people ask in astronomy and astrobiology?
Like having the background that I have,
Your specific life story, does that come into the questions that you ask, or?
Yeah. I mean, I certainly I do gravitate to the non-traditional types of planetary scenarios, climate scenarios, and I bet that's not a coincidence. This idea of, and I think it probably is a reason why the planets around M stars were particularly interesting. Not that planets around solar-like stars wouldn't be any less interesting. I mean, and a lot of people think that really looking for a planet around a sun-like star is the way to go, because you don't have to contend with a lot of complications that the M star environment can present, like stellar flare activity and all sorts of, the UV rays. But I think, yeah, there's an imagination that I hope I have. I think I have this ability to think outside of the box as a result of inhabiting different spaces, that allows me to think more broadly about this topic than I would otherwise.
So Vera Rubin, who was a longtime astronomer at Carnegie, and I was fortunate to be her colleague for many years, and a pioneer for women, and a mentor of one of your mentors at Lowell Observatory. So I thought that was a neat connection in your book. She told a story that her son would asked her once, do other mommies all observe, and do daddies observe too? Or is that something just mommies do? And so I wonder if any of your rising star girls have asked you, do white men do astronomy too, or?
That's what we're getting towards. That's what. Well, one of the first things we have the girls do the very first day of the workshops is draw a picture of what a scientist looks like. And I think when I first started doing these workshops back as a postdoc, what they would draw was like the picture that I showed you, the kind of wiry hair, the white guy and the pocket protector. But recently, we're in workshops when we've done these, what the girls are drawing are women, and women of color. So I think it's telling, and that's before we've even done anything with, in workshop wise. So it's saying that it's telling us that there are changes happening, that those changes are making their way to the girls, and I hope that continues.
Well, it's terrific. And I will ask you one last question. You seem like a very optimistic person. And so here's my question. Will we find that small planets around M stars have atmospheres with the James Webb Space Telescope and be able to say something about their climates in the near future?
You know, I didn't think we were going to be able to do anything with James Webb when it came to planets, certainly Earth-sized planets. And I think we've been surprised. In the last couple months, even, we've seen more information and learned more about planets, and we're getting close to the Earth's using Webb to be able to. We're starting to make temperature maps of the larger planets using Webb. And I think it's possible to be able to detect something with James Webb pertaining to an Earth-sized planet. Now, I think we're really going to need the next generation missions like HWO, the Habitable Worlds Observatory, or something with, along those lines. But that's a similar size mirror. It's like a 6.5 meter mirror. And that's what we need to use, dedicated to looking for these biological fingerprints of life in the atmosphere. So I'm optimistic. Yeah, you're right.
Excellent. I have a bet with a friend, which I won't tell you which side of the bet I was on, about whether we would find life on another planet in my lifetime. So which side of that bet would you take?
My gosh, what I've been saying is, if not mine, then I think it's very much possible that we could answer that question within my daughter's lifetime.
And let us hope that those lifetimes are long and productive, because we really enjoyed hearing about all your work today. So thanks very much for joining us.
So thank you, Aomawa, for a really, really nice talk. That was excellent. I think I'm going to use this. We record them. So we'll use this as an example. When someone says, how should I give a capital science evening talk? I'll defer them to you.
Thank you.
Let's all give Aomawa one more round of applause. It was terrific. And also let's thank Alicia for doing a great job in interviewing. Two people who love, we're lucky because it was a great conversation, but when two people who love exoplanets get together, they can go into a black hole.
We certainly could.
Nonetheless, I do have one question though, just to finish this up. It's my prerogative. You started with a bit of meditation. And I'm just wondering if that have you done that before?
Yeah.
Does that open people's minds to the complex concepts that you present? Do you feel like it does? Because I'm thinking about maybe I should do this. But do you think does it bring people closer? Do you think they can connect to what you're saying better that way?
I have found that it seems to help people get grounded in the space together.
To be here.
Yeah, to be here, to leave whatever happened out before out there, and whatever's going to happen after the talk in the future, and to all be together in the moment. And I feel that energy after we're done. It seems like people are more present. I feel more present when I do.
Well, that was a first for me, so thank you very much. Let's give them one more round of applause. Now comes the moment many were waiting for, the questions, which mostly Alicia asked, which ones came to the top. So I'm just going to quickly read the names, and what I'm going to ask you to do, you're going to win the book by Aomawa. Sorry. Sorry. And you just should pick it up. I think Natasha's in the back there. She's raising her hand. They were great questions. I do want to say I've been following the questions. This is a great group. So there are 4 people. There's 5 people. Marvin Jones, are you here? Yeah, good. You got book number 1. Danny, you get book number 2. Ed Fuch. 3. And Monique L. There you go. And then Bill Warren. Okay. Well, I want to congratulate you for getting good questions out there. And thanks to everybody for coming tonight.